I thrill at the sight of huge dinosaurs at the multiplex, as long as they don't chomp down on humans. Whoops. Oh well, lunch. But I suppose you need some sort of provocative behavior if these burly beasts are going to star in their own films. The speculative premise of this flick? Well, scientists have used dino DNA to bring these extinct animals back as a tourist attraction. But dinos don't need to play ill-tempered silver screen saurians with a taste for human flesh to be compelling. They achieved that on their own more than 66 million years ago. I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. On Big Picture Science, we give you the wide-angle view on science and technology, and you need a wide angle to view these dinosaurs here at the American Museum of Natural History in New York City. Once again, dinosaurs are stomping and snorting their way through your local movie theater, but these colossal beasts stole the show long before CGI brought them roaring to life in the Jurassic Park blockbusters. We turn this episode over to these impressive reptiles to clear up misconceptions about dinosaurs, find out why you shouldn't tease T-Rex about his puny arms, and why we've now entered the golden age of dinosaur discovery. I've got my comfortable shoes on and I am set to wander and explore. It's free-range dinosaurs.
If I want to see a dinosaur, I can, obviously, go to the movies, flip on the TV, or even look up the classic paintings by early 20th century American artist Charles Knight. But if Molly wants to see a dinosaur, she just has to crane her neck.
I have to look up and squint to find the head of this enormous herbivore called a Barosaurus. Its head is almost touching the ceiling of the museum. Millions have seen this iconic dinosaur skeleton and also the T-Rex near it. They are what greet visitors to the American Museum of Natural History, and for many people, these dinosaur skeletons will be the most memorable thing that they see here. This gentleman is wearing a shirt that actually says, "Ask me about dinosaurs," and he doesn't work for the museum.
Yes, as someone who is a paleontology student, I love to talk about dinosaurs, so I might as well wear it front and center.
What kind of dinosaur is on your t-shirt?
So this is a Triceratops horridus, a species of horned dinosaur from the late Cretaceous of North America.
That just rolls right off your tongue.
Of course.
And what is your name?
My name is Matt.
From where do you hail?
From Manchester, UK.
What do you like about dinosaurs? You're wearing them on your t-shirt, you're studying them, you're thinking about them all the time. What is it about dinosaurs that's so compelling?
Well, I've always been into animals. I was always into animals as a kid. And the thing is about dinosaurs, they were real. They're not monsters, they're not dragons. And the reality of dinosaurs as animals, real animals that once walked the earth and behaved like animals, is far more interesting than the Hollywood monster movie narrative that's being pushed these days. And there are very few things you can see in their anatomy that you can't find contemporary examples of, because that's how the tree of life is.
For example, birds. Birds are dinosaurs.
Of course. Yes, birds are dinosaurs. You can see it particularly well in the Allosaurus skeleton mounted just there. That is a bird leg. There is no other way of putting it. The structure of the toes, the structure of the femur, it is very much what you would expect for a bird. Even the arms, while they may not look like bird arms, straight away, they share the exact same configuration of bones. Dinosaurs can't rotate their wrists, they can't pronate their hands, which is something that birds can't do either. Although you can't see it in these skeletons, they would have had massive air sacs and pneumatized cavities which allowed the large bones to move and reduce their weight. And that's why dinosaurs were able to get so big, because despite the strange size and the strange look of them, they have very bird-like anatomy internally.
Or you could say that birds have very dinosaur-like anatomy, being dinosaurs as they are.
Yes, it depends how you want to look at it. You could say that birds are dinosaurs, or you could say that dinosaurs are stem birds.
Thank you very much.
You're very welcome.
To say that dinosaurs are stem birds, as Matt from Manchester was saying, well, that just means they're all part of the same group. So, of course, that includes all dinos and their descendants, birds. In other words, that robin in your yard is an avian dinosaur looking for a worm. It's an example of how the science of dinosaurs is at least as impressive, if not more so, than what we create in fiction. So in this episode, we'll give you an all-dino discussion with paleontologist Kenneth Lacovara, who dug up one of the most massive dinos of them all, Dreadnoughtus. There's this misconception that the dinosaur extinction event 66 million years ago somehow represents a failure of these beasts. They didn't adapt. But in reality, dinosaurs had global dominance for the better part of 165 million years, 230 million if you include the birds, and compare that with the measly 56 million years of primate dominance and 400,000 years of Homo sapiens, and you should feel truly humbled. Dr. Lacovara makes the case for why dinosaurs matter in his book with that title, and we begin our dinosaur discussion considering his polite request. Let's stop using the term dinosaur to refer to something outmoded or unsuccessful. Dinosaurs mastered all the environmental challenges that were thrown at them: drifting continents, shifting sea levels, fluctuating climate. To be a dino meant to be a master of adaptation.
That's right. When dinosaurs first evolve, we still have Pangea. And when they go extinct after that asteroid hits, the world's continents look pretty much like they do today. So you can imagine the immense changes that the planet went through during the era of the dinosaurs, and they were able to adapt and thrive during all of that.
Well, what are some specific adaptations that the dinosaurs went through so that they could survive under these shifting environmental conditions?
Well, initially in the late Triassic, they were tiny creatures, probably insectivores, little bipedal creatures. And the big scary animals at the time were crocodilians. There were all kinds of different crocodiles dominating the terrestrial habitats. And then there was an extinction near the end of the Triassic period, and the dinosaurs really got their chance to shine. Some of them stayed tiny, some of them evolved into small herbivores, and some of them got large, and then some of them got really, really large. And so we end up with the giant sauropods, the largest land animals to ever walk the face of the planet, the giant carnivores like Tyrannosaurus rex, and others that were the largest meat eaters to ever walk the planet. And, dinosaurs, they were active, vigorous creatures. And so what we can see in their anatomy is they hold their limbs under their bodies, more like a horse than like a lizard. And that tells us that these creatures were moving around in their landscape, maybe day and night, that they were traveling fast, that they were agile. And so, much more like the way a mammal behaves than like a lizard or a crocodile behaves.
Well, you should say more about that anatomy because it really is fascinating. And in fact, it's one of the ways that we can identify birds as being dinosaurs. But the idea is that the limbs are right under the torso, as opposed to a crocodile where they have the limbs splayed out. And if your limbs are right underneath you, as they are with dinosaurs and birds, another form of dinosaur, you can take off like a shot and run in a moment's notice. Is that the idea? It's just really efficient.
Yeah, that's right. If you think about the crocodile day or the lizard day, long periods of torpor where they just laze around. Their metabolic requirements are pretty low, so they don't need to eat every day, maybe once a week or once every couple of weeks. And occasionally they put on this blinding burst of speed where they catch their prey. That's not dinosaurs. The dinosaur day is much more like the mammalian day. They're up on all four limbs or two limbs if they're bipedal. Those limbs are right under their body. They're moving around. They're active. They're vigorous. They're burning a lot of calories. Therefore, they have to take in a lot of calories. So even though their name means lizard, dinosaur, terrible lizard, they don't behave very much like lizards at all.
Well, how fast were they? Because when you think of a dinosaur, you picture it, you don't think of it as an athlete necessarily or a fast animal, one that could sprint. How fast could they go?
Well, I think some dinosaurs were quite fast. There's a lot of disagreement among paleontologists when we talk about the speeds of dinosaurs. Some would say that a dinosaur like Gallimimus could run maybe 35, 40 miles an hour. There's a lot of disagreement about the speed of T-Rex. Some think that it could outpace an Olympic sprinter. Some think it was slower. If you imagine, look at an ostrich, look at turkeys. They are dinosaurs, and they are very fast, agile runners. And imagine the non-bird dinosaurs running along kind of like an ostrich would. Pretty vigorous creatures.
When I think of alligators, crocodiles, things like that, they're mostly lying around, but they're lying around in the sun. And I figure that's because they're cold-blooded and they don't have the They don't, they don't have the metabolism to keep their bodies, alive, that kind of thing. Whereas the dinosaurs, well, were they also cold-blooded? I mean, they had this much higher metabolic rate. Was that just an accident? Or did they, switch to being warm-blooded because that would give them this higher metabolism?
Well, certainly we know that some dinosaurs were warm-blooded because birds are warm-blooded and they are dinosaurs. But I think the concept of warm-blooded versus cold-blooded kind of breaks down when we look at dinosaurs in that some dinosaurs are so huge that they're going to run a high body temperature just by virtue of their great mass. And so I think for most big dinosaurs, their main metabolic challenge is shedding heat, not providing enough heat to stay warm. And so if you were to scale something like an elephant up to really big dinosaur size, up to 40, 50, 60 tons, that animal would literally cook inside of its own body. The flesh would cook because an elephant doesn't have the adaptations that would enable it to shed heat as efficiently as a dinosaur does. But think of a really big sauropod dinosaur like Brontosaurus. Long neck, long tail, so it gives it a lot of surface area per volume. And then dinosaurs have what we would call an avian-style lung. So they have a lung, but they have a posterior and an anterior air bladder, so one ahead and one behind of that lung, which allows them to circulate an immense amount of air within their body and gives them an immense ability to dump heat into the atmosphere. So they can shed heat by their neck and tail like a radiator. They can dump heat through respiration. And so they're able to keep cool with these super huge body sizes where mammals would not be able to.
In fact, you say if you want some ideas for how to build an advanced cooling system, look at the dinosaur for inspiration.
Well, that's right. And, dinosaurs achieve things that human engineers struggle with today, such as this really efficient and passive cooling system. They don't spend any calories cooling their body, and yet they're able to maintain a regulated body temperature. They can also, big dinosaurs are the champions at moving heavy loads over rough terrain. Dinosaurs achieved self-powered flight, and, you can look up attempts at human self-powered flight on the internet, and they're fairly feeble and often comical. And so, we have yet to achieve what dinosaurs were able to achieve in many areas.
One of the things that you point out is that the adaptive traits, the evolutionary traits that dinosaurs have adopted, some of the advantages are not so obvious. And when you look at the tiny arms of the T-Rex, he just looks like he has puny arms, and it feels sort of sad. But actually, it's a very smart from an evolutionary perspective. And why is that?
Well, that's right. In evolution, it's always use it or lose it. And every part of a body that an organism has a cost associated with it. And so there's a cost to grow it, there's a cost to maintain it, and there's a risk as well that body part, whether it's an eye or an arm, it could be injured, it could develop some pathological condition. And if it's not there, obviously those things can't happen to it. And so in the case of the ancestors of T-Rex, what we see are carnivorous dinosaurs that, look quite a bit like what T-Rex would eventually become, but they have much longer arms, long arms with big arm muscles. But even if you take an animal from a different lineage, but who people know, like Allosaurus, they have quite long arms, but an Allosaurus probably cannot reach its mouth with those arms. And while hunting, it probably can't see its arms. So I'm not sure that those arms would confer much of an advantage to an animal like that. And if the arms aren't providing an advantage, yet costs to grow, costs to maintain, and provide an area that can be injured, so increase risk, then that body part has to go. And so if there's variation, say, within a group of Tyrannosaur ancestors, some are going to be born with slightly larger arms, some with slightly less. If the arms aren't really conferring an advantage, the ones with the smaller arms are going to be more successful. They're going to use less energy and maybe have less injuries, and will be able, therefore, to pass more of their genes on into the future. And so what we see in time is that Tyrannosaurs get smaller and smaller arms. Evolution knocked off a finger as well, so they end up with these two little witchy fingers at the ends of arms only about as long as yours, on an animal that's the size of a bus and that weighs 8 or 9 tons. But it's interesting, this opens up another possibility for T-Rex, because T-Rex possessed the most powerful bite ever for a land animal. And if you're going to have a really strong bite, you need really big jaw muscles, and therefore you need a really big head. And if you're going to have a really big head, you need really big neck muscles to hold up that head. And guess what? Neck muscles and arm muscles compete for muscle attachment space along the bones of the shoulder. So you can't have both. And so as the arms of T-Rex got smaller and smaller, it cleared the way for the evolution of that super big head and really, really murderous bite.
You've written in your book, Kenneth, that if I like eating chicken, I like eating dinosaurs. And since everything tastes like chicken, I guess everything tastes like dinosaurs. I guess there's no reason to think that they would taste any differently than, anything else. We're all built of the same stuff. But on the other hand, when I go to Kentucky Fried Chicken, I don't think of it as Kentucky Fried Dinosaurs. What's the difference between a chicken and a dinosaur, though? I mean, how can you tell the difference?
Well, there is no difference. That's kind of like saying, what's the difference between a camel and a mammal, right? And so the reason that a camel is a mammal is because it has the very first mammal for an ancestor. And the reason that a chicken and all birds are dinosaurs is because just like T-Rex, just like Stegosaurus, they have the very first dinosaur for an ancestor. And if you have the first dinosaur for an ancestor, you are a dinosaur.
But what's interesting is if we picture a flying dinosaur, we picture a pterodactyl. I mean, one does, you don't. And a pterodactyl is not a dinosaur.
They are not dinosaurs. Your children's books have lied to you.
What is it?
The pterosaurs, they branch off before there is the first dinosaur. They're in a bigger group called Ornithodira. So dinosaurs and pterosaurs have a common ancestor, but that ancestor occurs before the first dinosaur. And therefore, if you branch off of that, you can't be a dinosaur. You're outside that group. Same with the big sea monsters like the mosasaurs and the plesiosaurs. They are not the dinosaurs of the sea. Those are marine reptiles that have a common ancestor with the ancestors of dinosaurs, but again, before dinosaurs. And the same with crocodiles. They branch off before there is the first dinosaur.
So crocodiles are not dinosaur descendants, whereas chickens are.
That's right. Well, I wouldn't say that chickens are dinosaur descendants. Chickens are dinosaurs.
Chickens are dinosaurs.
Okay, well, I'm sorry. But, but Kenneth said if you have a common ancestor that was a dinosaur, you are a dinosaur, right?
That's true.
We'll be back with Kenneth Lacovara and dinosaurs and talk about his work in the field. How does that sound, Kenneth?
Sure, sounds fun.
Okay, but can you leave us with one tantalizing dinosaur fact?
Well, the first Tyrannosaur discovered was not Tyrannosaurus rex. There are about 24 other kinds of Tyrannosaurs, and the first one found wasn't found in some windswept plain in Wyoming. It was found among the tomato orchards of southern New Jersey, a Tyrannosaur called Dreadnoughtus, found in 1866.
And that's a perfect plug for paleontology in New Jersey, which we're going to come right back to.
You're listening to Free Range Dinos on Big Picture Science. The terrifying titans, otherwise known as dinosaurs, are roaming freely throughout this episode of Bi-Pi-Sci, and Molly is finding some of them as she roams the historic halls of the American Museum of Natural History in Manhattan.
Hi, I'm Edwin.
Edwin, do you have any dinosaurs here at the museum?
Oh, we have lots of dinosaurs. Dinosaurs from every dinosaur period, from the earliest to the end of the Jurassic period.
What's the most asked question about dinosaurs that you get?
Where's the T-Rex? Where's the T-Rex is definitely the most popular one.
I'm looking at a second skeleton of a Tyrannosaurus rex. This T-Rex skeleton is one of the few real specimens of T-Rex on public display. Because it's so expensive to put real dinosaur bones on display or fossilized bones on display, most museums display a cast of the fossils, but these are the real fossils. And I have to say that the arms of this T-Rex are quite impressive. or at least in skeleton form. They're still quite large. I don't think I would want to wrestle with a T-Rex and test whether or not his puny arms are also weak arms. But that jaw and those teeth are truly something spectacular and frightening.
Yeah, not quite so frightening as during the Jurassic, when Molly would merely be a T-Rex hors d'oeuvre. But when you look at the bones of a dinosaur in a museum, the exhibit kind of gives the impression that entire skeletons were found in the ground just waiting to be bolted together to be put on display. But in fact, most dinosaur bones don't come neatly packaged in a box labeled "Some Assembly Required." These stacked up skeletons are the result of years of hard work by paleontologists in conditions that are alternately hot and sweaty or freezing cold, depending on the location of the dig site. Kenneth Lacovara endured the latter, really cold, to bring to public display the fossilized skeleton of Dreadnoughtus, the most massive beast known to have stomped across the continents of our planet. But before we travel to Patagonia to check out the story of Dread, we visit some of Dr. Lacovara's dino digs that are closer to home. Kenneth, you grew up in New Jersey. You're now the founding dean of Rowan University's School of Earth and Environment, and the Edelman Fossil Park is also there. Some people may be surprised to hear that New Jersey has a bonanza of dinosaur bones, the cradle of dinosaur paleontology. You know, I went to Dinosaur National Monument. I believe it was in Wyoming when I was a kid. That's a long way from New Jersey. Why all the dinos in New Jersey?
Well, there's dinosaurs in New Jersey for the same reason there's dinosaurs anywhere. You have to have rocks of the right age, and they have to be sedimentary rocks, and then you have to have an exposure of those rocks so that you can see the fossils that they bear. And it turns out that these conditions were first really encountered by people. First in Britain, where the first scrappy dinosaurs were found, and they get that name in 1842 from a British anatomist, Sir Richard Owen. He calls them dinosaurs, meaning terrible lizards. Fast forward to 1858, that's when the world's first nearly complete dinosaur skeleton is found, and it's found in a town called Haddonfield, New Jersey. And it turns out to be a duckbill dinosaur named Hadrosaurus folkii. And it's found there because New Jersey has Cretaceous-age sedimentary deposits, and people used to dig up what farmers call marl. Marl it's not a geology term, it's a farmer's term, but it's a kind of fertilizer that used to be very popular. There were thousands of marl pits up and down the East Coast, and so people started discovering dinosaurs in these marl pits. In 1866, the world's first Tyrannosaur is discovered in Mantua Township, southern New Jersey. That's a dinosaur known as Dreadnoughtus today. And then other dinosaurs found in these sleepy agrarian towns throughout South Jersey. So New Jersey is really the cradle of dinosaur paleontology.
But it has not very much to do with the dinosaurs themselves then. I mean, it was just that this is where people were digging things up, and they happened to hit the dinosaurs, right?
Dinosaurs were cosmopolitan on every continent, including Antarctica. So it's not that they uniquely occurred there, it's that we have the preservation and some unique windows into that time there.
Well, Kenneth, about a dozen years ago, you discovered the bones of a massive dinosaur, not in North America, it was in Patagonia, which you named Dreadnoughtus. I think it weighed something like 65 tons, which was the equivalent of a dozen elephants. And I wonder if you could just give us an introduction to this dinosaur, what makes it so special, and then we'll talk a little bit about how you found it and what it's like to be in the field. So introduce us to Dreadnoughtus.
Sure. Dreadnoughtus was 85 feet from snout to tail. It stood about 2.5 stories at the shoulder, and all fleshed out in life, it would have weighed about 65 tons. So as you say, that's the mass of a herd of elephants. That's the mass of about 8 or 9 T-Rex. That's about 10 tons heavier than a Boeing 737.
And what would it eat? I mean, it requires quite a bit of food, I would think, to keep that thing going.
Well, it does. You can only get that big if you eat plants. I mean, when you think about it, all the energy in an ecosystem is created by photosynthesis. And so that's where most of the energy lies. And there's a general rule in ecology that when you transfer from one feeding level to the next, you leave about 90% of the energy behind. So if you want to be either really big or really numerous, you have to eat plants. You have to feed low in the food chain. And so Dreadnoughtus, like all the supergiants, ate plants, and I'm sure it had a lifelong obsession with eating, and I'm sure its day went pretty much like stand around, and with that long neck, you can clear out a huge envelope of plants, taking in tens of thousands of calories while expending very few. Do that for an hour or so, take a few steps to the left, and do it again. And I think that's mostly what they did.
You know, when scientists say they've unearthed the new dinosaur fossil, or at least by the time it makes headlines, it feels as though to the reader that the discovery happened suddenly. It happened last weekend, or this is what they did last month. But actually, there are many years between the initial discovery of a bone and the moment when the public learns about it. And I wonder if you could take us through that a little bit and the process by which Dreadnoughtus was uncovered and then brought to public eye. For one, you spent many austral summers, that is, summers in the southern hemisphere near Antarctica, in a tent looking for this guy or looking for something. Is that right?
That is right. It never feels sudden to paleontologists. It's a pretty long and arduous process. And so I spent a field season down there prospecting for bones in 2004. And then in 2005, I discovered first the femur, the thigh bone of Dreadnoughtus. And unlike most bones that you find that are either fragments or isolated bones, this thigh bone was connected to the shin bone. And then we had about 10 bones exposed after the end of the first day. And then 4 field seasons later, we had about 145 bones exposed. And it's right down at the bottom of Patagonia near Tierra del Fuego. The weather is always terrible there. The wind never stops. My first year down there, I provisioned cereal for the crew to eat for breakfast. You can't eat cereal for breakfast in Patagonia because it blows off your spoon before you can eat it.
And sometimes if you want to get a drink of water, you stick your head outside the tent and the water's frozen.
Actually, the water inside my tent would be frozen on some mornings.
Kenneth, other than the discovery of this dinosaur, and we're going to say more about that, what is your most, and your cereal blowing away, what is your most vivid memory of this time that you spent in the tents in the cold?
You know, it's really the work. And I love the work. Most paleontologists love the work. And, life is really simple when you're out in the field. You wake up, you have a meager breakfast, you hike up to the quarry with some pickaxes and other hand tools, and you start breaking rock. And in that very simple process, using things that you bought at the hardware store, you're traveling back in time and you're seeing things that no human has ever seen before. And you're learning things that no human has ever known before. And when that's occurring, all the discomfort and the hunger and the food poisoning and the cut and bruised and blistered hands, that doesn't matter anymore because you're time traveling to past worlds. And it's just an amazing feeling. And I can't get enough of it. When I'm not doing it, I long for it every day.
And I'm wondering if you knew what it's like to find a dinosaur bone. Your eyes are just scanning the ground. This is what I imagined, scanning the ground. And then do you know when you've seen something? Is it sticking up out of the rock? How do you know when you found a dinosaur bone? And how did you know that you had found this thigh bone?
There are times when you will see most of a bone exposed. That's pretty rare. And you never just walk up to a scene like you'll see in Jurassic Park and see a whole skeleton laid out there in the desert like that. Usually what you will see is a tiny patch of bone. And I saw a patch of bone about the size of a tea saucer.
And it looks like bone. It looks like bone.
Well, you have to check. A lot of what we do in the field is bone, no bone, or bone or fossil wood. It's hard to tell when you only have a little patch exposed. It's easy when you see the whole bone. So I saw a tiny patch of bone exposed, which you do when you're in the right geological circumstance. That happens every 10 or 20 seconds. So, I wasn't too excited about this. Bent down, started brushing it off, and it looked like, oh, that's bone, that's nice. And it started to go somewhere. And I thought, well, that's pretty interesting. And then after an hour or so, we had the whole femur uncovered, which right up on the surface, the sediment is pretty weathered. So it's easy to work fast on the surface. It gets much harder when you go down a few feet. But even then, once we had this 6 foot 3 inch femur exposed, I wasn't too excited because it's very, very common to find an isolated bone. And a femur is not a diagnostic kind of bone. You're probably not going to be able to tell who it belonged to if all you find is a femur. And then we found the shin bone, the tibia, and the fibula under that. And then we started to uncover vertebrae. And now it's got my attention. Now I'm pretty interested in it. And I can see that it's one of the largest animals that has ever been discovered. But quite probably I would never know who it was because I would never find the bones that have the diagnostic information in them. But as we uncovered more and more of the skeleton over that season and over 3 more field seasons down there, then I knew we had enough that we would be able to know for sure whether it was a new species or not. But you still don't know that answer until you get it into the lab, open up the plaster and burlap jackets, take the remaining rock off, and then really start to study the anatomy. And to assert that it is a new species, you need to find at least one feature in the skeleton that is unique to it, that isn't possessed in that way by any other dinosaur. And in the case of Dreadnoughtus, we actually found 8 features, which we call autapomorphies. We found 8 of those that show that it is a unique genus and species of dinosaur.
And you said you did not let yourself feel excitement initially. When did you let yourself feel excitement, and what does it look like when a paleontologist, when you feel excitement about a find?
Well, by the end of that first day, we were pretty excited because we knew we had found a substantial skeleton of a giant plant eater. We hiked back down to the camp, which was a tent by this roaring glacial stream. We fished some cans of Kilmay's beer out of our rock pen refrigerator in the river and had a little celebration that night.
Okay, so you open up a beer. You don't throw your hat in the air or do a jig? Okay.
Not that I recall, no.
What would a predator attack if it did attack a Dreadnoughtus? Would it just try and bite it in the neck or maybe just bite that tail?
Well, I can't really imagine that a predator is going to attack a full-grown Dreadnoughtus. Now, a baby Dreadnoughtus, that's a different story. They're the size of a house cat, and so they would gobble up baby Dreadnoughtus like M&Ms. But I don't think you'd want to mess with a full-grown dread.
Now, Kenneth, we have a couple questions from listeners we asked, posted on our social media that we'd be talking with you, and I'm just going to give you 2 of those questions. The first is, how is it that paleontologists are able to speculate about dinosaur behavior at all?
Well, there are a few ways. One is that we do have some living dinosaurs. Those are the birds, and so we can actually observe the behavior of some dinosaurs. We can get behavioral information by looking at the teeth of dinosaurs, much the way you can do that with mammals today. And so we can see if they were eating plants or if they were carnivores or if they were omnivores. We can get some behavioral information from looking at the nests. There are examples of dinosaur nests where you can see that all the eggs were crushed into little shell bits. And so, that suggests that these babies are hanging out in the nest for a good amount of time. There are other dinosaur nests where you see a perfect bottom of the eggshell, and the top is gone and the baby dinosaur is gone. So that suggests that these dinosaurs were precocial, that they hatched and they just took off and went about their lives. There's also trackways, and so we can see behavior from trackways. There are beautiful tracks of hadrosaur dinosaurs on the face of Denali in Alaska. And there you can see tracks that suggest multi-generational herds of dinosaurs traveling together. So, it's detective work, really. We're never going to have a complete understanding like we do of animals that we can observe today, but I think it's remarkable what paleontologists have been able to piece together so far.
And the second question, we have heard about the benefits of looking for fossils in New Jersey, but one listener wants to know, what is the best place in the Midwest to bring children to look for fossils?
Well, if you want to just say fossils in general, there are wonderful fossil deposits in Ohio around Cincinnati and Cleveland. These are older rocks from the Paleozoic where you can find really cool fossil fish like the armored fishes and invertebrates.
What about dinosaur fossils?
See, the problem with that is that sea level is very high during the Mesozoic, during the time of the dinosaurs, and the Gulf of Mexico inundated North America, came up right through the middle of the continent and connected to the Arctic Ocean. So the Midwest during the time of the dinosaurs is a sea. So you can go down to places like Kansas and you can find really beautiful fossils of mosasaurs and plesiosaurs, and so marine reptiles, but you're not going to find the dinosaurs there because all the dinosaurs lived on land, so they would either be to the east in the province we call Appalachia, or they would be to the west along the ancient coastline in Colorado, or further west in Utah and Montana, places like that.
We'll be right back with Kenneth Lacovara and talk about Jurassic World, the movie, and why today is the golden age of dinosaur discovery. Kenneth, can you leave us with one dinosaur fact for my next cocktail party?
I can. You, Seth, could actually take a velociraptor. A velociraptor is only about the size of a turkey and has a skull that's maybe 10 inches across.
But they can jump across the furniture in the movies.
They can, but if you have a velociraptor in your kitchen, it's really more of an opportunity than a problem.
I'll just check my cookbook.
And we'll find out how accurate those dinosaurs are in the movies. You're listening to Free Range Dinosaurs on Big Picture Science.
Let's face it, dinosaurs are showstoppers. Their cinematic appeal is a dependable source of terror and awesomeness as they stomp and roar their way across the silver screen.
These creatures were here before us. And if we're not careful, they're gonna be here after. Welcome to Jurassic World.
The dinosaur movies are fun, but as we're hearing, the actual beasts do more than just provide thrills and chills. Dinosaur fossils can help us piece together our planet's geologic and biologic history.
Chris, you have a dinosaur t-shirt on as well. It looks like you're doing some promotional activity for the latest film in the Jurassic Park series.
It's a parody of the Jurassic Park logo from a joke from an old Simpsons episode called Billy and the Clonosaurus.
Tell me what you appreciate most about dinosaurs.
I actually work as a geologist, and although I'm not that much into paleontology, I really like things to do with Earth history and how things have changed throughout time.
Dinosaurs are found in rock. Dinosaur fossils are found in rock. And how do we use the rocks to date the dinosaurs, to find out how old the bones are?
Well, dinosaurs and other fossils, different species will exist at different points in time. And so if you find certain species in one rock bed, you can use that as a marker across different regions. And once you've got a picture of the entire region's worth, you can build up an entire column, as it were, of different layers of rocks throughout the Earth's history.
Thanks a lot.
You're welcome.
When paleontologists like Kenneth Lacovara dig through those layers of sediment, they're traveling back through time. And these days, paleontological discoveries are coming at a brisk pace. Dr. Lacovara and others say we're in a golden age of dinosaur discovery, with as many as one new species uncovered every week. And that means we're better able to separate dino facts from dino fiction. So the latest film in the Jurassic Park franchise is opening in the summer of 2018, and with lots of cool new dinosaurs, many of whom seem to be kind of ornery. Would it actually be a good idea to create a Jurassic Park if we could do that, Kenneth?
Well, I'm not sure that would be a fabulous idea. It would be really interesting, and I'm not sure that it would be possible. The problem is that DNA is a water-soluble molecule, so we don't know that it could hang around that long. So far, the oldest DNA recovered is about 800,000 years old from a Pleistocene polar bear, and 800,000 years is essentially now in geological time.
So we don't actually have the genetic code of these guys, and that alone would not be enough, right? I mean, maybe you would try and clone that very ancient bear or a mastodon or something that we actually do have some DNA from, but, you need an animal around today to gestate that critter, right? You just can't go into the lab with the DNA and come out with a dinosaur.
Well, that's right. You have to get the DNA into a working cell, and then you have to get that cell into, in the case of a dinosaur, into an egg. And we don't have the technology for that today, although people are working on de-extinction, in particular with the mammoth. And, the mammoth having gone extinct not all that long ago, we have its complete genome, and I actually think that the mammoth may be brought back at some point.
one thing that I believe I read in some literature not too long ago is that this picture that you often see of a big dinosaur, a big carnivore dinosaur, roaring and stomping its feet might not be entirely accurate because they might not have been able to roar. Is that true?
Well, that is true. Dinosaurs have different anatomy, and think more bird when you think dinosaur rather than big beast like a bear. They don't have a larynx like we do. They have an analogous organ called a syrinx. So paleontologists have speculated that a T-Rex probably made more like bird sounds, more like chirping or whistling or sounds like that. They were big, so they were probably deep sounds and probably loud, but they probably didn't roar like portrayed in the movies.
Well, the dinosaurs that we see in the movies are impressive, but the dinosaur finds in real life are even more so. And it turns out that we are uncovering more new species now at a faster pace than we were. Something like 31 new dinosaur species were found in 2016. There are dozens found every year. Kenneth, what are the reasons that this seems to be the golden age of dinosaur discovery?
Well, there are a couple reasons. One is that the world is freer now than it was in the past. So it's possible to go to places where we could never go before. And so, China has opened up to paleontologists. Mongolia has, places in South America that hadn't received a lot of attention, North Africa. So we have more places where we can dig now, and there are more paleontologists. If you think about world population, as it grows, some small percentage of the population are going to be paleontologists. And as the population grows, there are just more and more of them. So we have more people with more boots and eyes on the ground than ever before in more places. And the result is that we are finding more and more dinosaurs. So if you go back 100 years ago, there was a new dinosaur species about once a year. If you go to 1970s, it was about a half a dozen a year. Now it's almost one a week. It's really hard to keep up.
You mentioned China, and there seem to be many, many species coming out of China, in particular in one region that is opening our eyes to the distinction between dinosaurs, non-avian dinosaurs, and avian dinosaurs. That's birds today. What are we learning now from China and these fossils?
Yeah, that's right. I think you're referring to the Liaoning province, which is in the northeast of China. During the time of the dinosaurs, there was a continental environment there with lots of deep lakes, and these tiny little dinosaurs were ending up in the lakes, sinking to the bottom and being covered by very, very fine-grained sediment. And you can think of the size of the sedimentary particle as kind of like the resolution on your computer screen. So the finer the particle, the better resolved the fossil is. And so we see these tiny little dinosaurs from there. They're not birds, but they have feathers, but they have all the other dinosaur traits that you think of. And we see feathers first evolving as what looks like down. And that suggests that the first function of feathers was for insulation, which makes sense. If you're really big like a Dreadnoughtus, you can keep your body temperature high just by virtue of your great mass. But if you're a tiny little dinosaur, the size of a crow, say, you're not going to be so efficient with the way that you keep your heat. You're not going to have so much insulation. And so those downy kinds of feathers could help you regulate your body temperature. And then we see the evolution also from fossils in China of the pennaceous feathers, those long flat ones, which appear to be for display. And then we see dinosaurs that look like they have the ability to glide, but you can see they don't have the muscle attachment spaces for actual flight muscles. And then finally we get Archaeopteryx, which is first known from Germany, which looks like the first powered flying dinosaur, and that happens about 150 million years ago.
Kenneth, if I go into the forest today, if I can find a forest, most of the critters that I find there are going to be mammals. Not all, they're snakes and other things, but, the birds. But, you could say, all right, the mammals kind of dominate. Now, the assumption is if I went into that forest 100 million years ago, most of the critters would be dinosaurs. That asteroid, if it was an asteroid, maybe a comet, that wiped out the dinos and 3/4 of everything else 66 million years ago, if that had arrived at the orbit of the Earth, like an hour earlier, it would have missed the Earth. So my question is, suppose that had been the case, would I find dinosaurs all over the place now? Would there be dinosaurs sitting here instead of me?
I think so. Dinosaurs are around for most of the Mesozoic. They're doing great. Their biodiversity is expanding. They're on every continent. And then that asteroid hits and wipes them out, except for the birds. And if you think about it, asteroids, they all form at the beginning of the solar system, right? So that asteroid is 4.5 billion years old. So it's out there. It's out there when life on Earth starts. It's out there when the first dinosaur evolves in the late Triassic. It's out there when Dreadnoughtus is chomping around. Always there, circling the sun. And then one day the paths just line up and that thing hits the Earth. If you were to just throw a pebble at that asteroid when it's out, at the orbit of the asteroid belt, it misses the Earth by a wide margin. And dinosaurs, 165 million years, why not another 65 million more? There's no reason to think that us mammals who lived in the hidden and forgotten recesses of the dinosaur world for all that time would have ever gotten ahead.
Well, finally, Kenneth, we know that dinosaurs are interesting. That is part of your argument, and people are mad about dinosaurs. You don't have to convince them that they're fascinating beasts. But your thesis is more than that. It's something that you write about and that you've talked about, and that's that dinosaurs also are instructive to us from an evolutionary point of view, and they say something to us about our changing planet. And I wonder what the meta message is about dinosaurs for humans.
Yeah, well, I call the book Why Dinosaurs Matter, but I could have just as well called it Why the Past Matters. And the past matters because the future matters. We're all concerned with the future, with this environmental future that we're flying into, but we don't have access to the future. We can do no experiments in it. Nobody remembers the future. The present is really nothing, right? The present is gone as soon as you can think of it. So where does our information come from? Well, it comes from the past. All of it comes from the past. And it was Winston Churchill who said that the further back you look, the further ahead you can see. And the Earth has gone through convulsions before. The Earth has gone through climate changes and extinctions and ocean acidification and toxic events that laid waste to entire landscapes. Mostly these things have happened much slower in Earth history. They're happening very, very rapidly right now because of human activity. But we can look to the past and we can see what happens when these perturbations and disturbances occur, and it will help us make our decisions going forward. And so I think, it would be really foolish and arrogant of humans to ignore the rich rock record that precedes us that may help us out of the pickle that we're in right now.
Kenneth Lacovara is the founding dean of Rowan University School of Earth and Environment. He is also the founder and the director of the Edelman Fossil Park of Rowan University. He is a paleontologist. He has unearthed some of the largest dinosaurs ever to stomp across our planet, including the supermassive Dreadnoughtus. And if that's not enough, he is also the author of Why Dinosaurs Matter. And I think he's made a very strong case for that over the course of this hour. Kenneth, thank you so much for speaking with us.
It's been my pleasure.
It certainly is tempting to regard the dinos as a special time in Earth's history, and indeed they are. Because, sure, if you looked at our planet from far away, at any random time, you'd had an 80% chance there wasn't anything bigger than a microbe. But for 150 million years, there were these big dinos. I guess the trilobites could say, well, we had more than that, and indeed they did. But, Homo sapiens likes to look at itself as the crown of creation. Well, it's just a little tiny bubble on the top of creation compared to these guys. They were really successful, and that kind of makes me wonder if we were to go to a random other planet somewhere that had life, we kind of expect it will be something that sort of looks like us, but maybe it would be something that looks much more like a dinosaur, or obviously a good design.
I'm now descending the stairs from the 4th floor dinosaur exhibit, and I have to say I'm feeling some sadness saying goodbye to these impressive animals. But I'm comforted by the fact that I can always come back, we can always visit the dinosaurs, and that when we do, because of the rate of discovery of new fossils and new species, they may have to build another wing to the museum. Thanks to the team whose enthusiasm for producing Big Picture Science never goes extinct, senior producer Gary Niederhoff and operations manager Barbara Vance, and a special thank you to the American Museum of Natural History here in New York City.
Thanks also to financial support from Rena Shulsky-David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life. And a big thanks also to our listeners. Your ears have been attuned to a Big Picture Science episode called Free Range Dinosaurs. And if you'd like to hear more Big Picture Science episodes, you'll find them in our archive at bigpicturescience.org. You can also find links there to our guest, Kenneth Lacovara. And if you never want to miss an episode of Big Picture Science, subscribe to BiPi-Sci on iTunes, Google Play, Stitcher, Spotify, or iHeartRadio.